Bow your heads, please.
Dear Heavenly Father, we thank you that we are all here safe at Heed. We pray that today is a good day, and we thank you for Ms. Frady who has taken the time to teach us about weather and everything else about God's earth. Amen.
Amen. Thank you very much. Okay, so we are in our weather and water. So let's open your book if you don't have it out already. And let's start on page 8. And on page 8, it tells us that we can have a Christian view of weather. And honestly, I think we should have a biblical view of everything. And if the Bible's true, which it is, then it should permeate everything that we see and everything that we think. And it changes how you look at things if we know what it says in our Bible. And so you guys know this already because we've talked about geology and how it changes how we look at the rocks, you know, and somebody that doesn't believe the Bible thinks everything's billions of years old, whereas we look at it and go, no, I think that was laid down during the flood, and that was only about 4,500 years ago, you know. So it just makes a big difference on how you look at things. And I was going to ask you guys to do the weather reports on here, but then I personally couldn't get it to download from the website, so I didn't want to ask you to do something that I couldn't do. So I looked up a few different weather reports from around the country this week, just to give us an idea of what it looks like compared to us. And I really only got a couple of pieces of information. But here in South Florida, this week it's been averaging about 60 degrees in the morning and, excuse me, depending on where you live, between 80 and 87 degrees in the afternoon. So that's winter for us, isn't it? If any of you are watching from someplace else, you're thinking, what do you mean that's January? That's what it looks like in January in Florida. We're all kind of waiting for a little more cold weather, aren't we? But not the frigid cold. We just don't need that. But it's been nice. But in New York, during the same time, the average temperature has been 40 degrees. And here it's been clear, there it's been overcast. And in Chicago, 43 degrees. Chicago is one of the coldest places I personally have ever been. And when the wind blows there, I like Chicago, don't get me wrong. I mean, it's a neat city. But when the wind blows there and it's cold, it feels like it's going to cut you in half. Because it comes right off of the lake, and you know it's right on the Great Lake there, and it just, it's so cold. I've been there when the wind chill factor was something like -7, and I thought, oh, people die in that kind of weather. You know, I just can't relate to that at all. But anyway, so in Houston, Texas, it was around 63. That was the average temperature. In San Francisco, 54. And so you see that depending on where you live, the weather can be very, very different. And that was the point that they were trying to make here because we're studying weather. And we will study the difference between weather and climate and things like that as we go along. Let's go ahead and turn over to the next lesson, lesson 2, which in the 4th edition is on page 10. What page is it on yours?
11.
11, okay. And so on page 10 in the 4th edition, 11 in the 3rd edition, we're looking at the structure of the atmosphere. And so we're actually looking at, what's the atmosphere? What is the atmosphere? How did it define the atmosphere? Yes?
It's, there are the layers of gases around the planet.
Very good. When you have gases around a planet, or even a moon, believe it or not, there's a moon in this solar system that we know of that has an atmosphere. So if there's a blanket of gas around a planet or a moon, it has an atmosphere. And our planet has a very specific atmosphere, perfectly designed for life on planet Earth. If it was altered even slightly, it would be very, very dangerous. We were told in here, and I can't remember which chapter it was in, and shame on me because I read it all, but we were told, it is in this chapter, good, that our atmosphere is made up, and you'll have to memorize this when you're in physical science, our atmosphere is made up of 78% nitrogen, 21% oxygen, and 1% other. There's a variety of other gases. Now that means that if we had a pie, these percentages, in case you're uncomfortable with them, it means that most of the pie would be nitrogen. and then a little under a quarter of the pie would be oxygen, and then you have 1% other. And what we're talking about here when we do this is dry air. You've taken the water out of the air. So here in Florida, we'd have a lot of water in the air too most of the time because we have very high humidity. But here we're talking about dry air, and that's what the atmosphere is made up of. Now this is very, very important because I don't know about you, but when I was your age, I always was taught that we inhale oxygen, we exhale what? Carbon dioxide. That's one of those others, okay? We inhale oxygen, we exhale carbon dioxide. So I always thought that the air was made up of mostly oxygen. Be honest. How many of you thought that too? Okay, I did, because that's all I was ever taught, right? I mean, what do we need nitrogen for? As a matter of fact, nitrogen is a couch potato gas. The technical term for a couch potato gas is an inert gas, I-N-E-R-T, inert. Now, what does a couch potato do? Sits around and does nothing. So an inert gas is one that doesn't react with anybody else. It sits around and does nothing. And you know what? That's really, really important that our atmosphere is made up of a couch potato. Because if the oxygen percentage was higher, and let me get my glasses so I can actually see. There we go. If the percentage of oxygen were higher, just a 1% rise. Okay, that's not much, right? So if it was 22% instead of 21%, you ready for this? 70% more forest fires. 70% more forest fires. That would be devastating, wouldn't it? That's just with a 1% change. If the atmosphere was 31% oxygen, there would be 7 times more natural forest fires, and it would burn our bodies up. We couldn't live in it. Because if you have too much oxygen in the atmosphere, it actually causes blindness. It causes our bodies to burn up. Have you ever heard of a musician called Stevie Wonder? He's a very gifted writer as well as he sings and plays, but he's an extremely gifted, talented writer. He's blind, and those of us that are my age, we think of Stevie Wonder as sitting at the piano, because he's blind, and he does this as he plays, It's just a really talented guy. He's blind because when he was born prematurely and they put him in a incubator with straight oxygen, and it caused his blindness. So, and we didn't know that then. Like in the 60s, they actually, one of the NASA programs put the astronauts in a totally oxygen atmosphere, and it blew up. It's extremely combustible. So, and that's what it does to our bodies, is it burns it up. So if you have something that's even 1% higher, it causes a lot of problems. If you have a 10% higher, it increases the problem so that nothing could basically live that we can think of here on planet Earth. So what would be logical for God to do if we needed oxygen in the atmosphere, but if you have too much, it kills everything or hurts everything? So what do? You dilute it. What do you dilute it with? Something that won't do anything. Do you see the genius of what God did? So he diluted the oxygen with a couch potato gas called nitrogen. Not only that, but nitrogen actually protects us from gamma rays. Because nitrogen, you notice I wrote it there as N2? Nitrogen, the molecule nitrogen. Oxygen is 2 oxygens attached to one another, and they share 2 pairs of electrons. That's what those lines mean. Well, nitrogen is 2 nitrogens hooked together, but they share 3 pairs of electrons, which means they're bound together more tightly. When certain high energy rays called gamma rays come into the atmosphere from the sun, this triple bond actually absorbs the energy so that it doesn't kill us. Isn't that cool? Isn't that cool? And you guys heard, you read, we're going to talk about the ozone layer. Ozone is O3. It looks like this. Well, this bond is actually what absorbs the ultraviolet radiation in the ozone layer, and it's broken, and that's how God protects us from the ultraviolet radiation, the really deadly stuff. Some of it gets through, and that's what causes us a tan or a sunburn, right? But some of it is absorbed here. And then I'm pretty sure the oxygen itself absorbs a certain amount of the X-rays from the sun. The sun actually would kill us if it wasn't for the the atmosphere. The way the atmosphere is designed, it actually protects us from the killer rays that the sun puts out so that we can actually benefit from the sun without being killed by it. And didn't I go through the 7 ways that the sun we're protected from the sun when we studied it, when we did the our universe? And I told you that the sun, we're protected from the sound of the sun by the space in between, and the magnetic field of the earth protects us from the cosmic radiation. Did I go through that with you guys? I did. I thought so. Protects us from the cosmic radiation, and then the atmosphere itself, the way the atmosphere is designed, protects us from several other forms of radiation that would kill us, that come from the sun. So by the time it gets here, the sun actually benefits us, unless, of course, you sit out in it way too long, but otherwise it benefits us. And so we're protected by this cool design that we see that God made. Now, I just told you that things would burn up if there was too much atmosphere. Oxygen in the atmosphere. Let me see if I can pull this off. I'm going to try. Let me see if this works. And I can tell you're a pyro, so do me a favor and just light my candle for me, please. And what I'm going to do is there's hydrogen peroxide in here. Hydrogen peroxide is actually its chemical formula. You guys tell me, what's the chemical formula for water? H2O. It means there's 2 hydrogens attached to an oxygen. Hydrogen peroxide is H2O2. It's water with an extra oxygen attached to it, okay? Thank you. Now, first I want to show you, and you're going to have to light this for me again, sweetheart. First I want to show you that if we burn and we take away the oxygen, about a teaspoon. Let's see if I can get this in here. It's always tricky. Oh. Okay, no holes. Okay, what happened to my candle? Very good. The fire can't continue because it ran out of oxygen. When you put yeast with hydrogen peroxide does degrade over time, so I may have to use a new bottle. I bought a new bottle just in case. Yeah, I think I'm going to have to use a new bottle. Okay, it's cool. I'm going to make quite the mess here. Just want you to know that beforehand. Thank you, sir. Okay. Guys, pass me the garbage can, please. I know it's coming here. All right, we're going to use this bottle, but we're going to put in it fresh hydrogen peroxide. Because what happens is over time, hydrogen peroxide actually loses its extra oxygen, turns into water. It doesn't last forever. That's why it has to stay under pressure. I wouldn't. Seriously. He said, can you drink it? There are people that actually believe drinking hydrogen peroxide is good for you. I don't see that in the Bible anywhere, so I'm kind of going to stay away from that one. Okay, let's see. Oh, and we're going to loosen the balloon up a little bit that way. Let's see if we can make some oxygen now. Come on, yeast. Maybe I need more yeast. That may be what I need.
Yeah.
Let's see if that's what I need. Because it's supposed to. Wow, I wonder if my yeast is dead. I just don't think in those terms. Baker thing and all that. It's not that old. There it goes. Where's the. There they are. It may work. Okay. Hey, this one matches my dress. Okay, here we go. I have made quite the mess up here already. All right, we're going to use that one because it's at least starting to try to help me. Yeah, they're starting, so we'll get that over there. I want you guys to be able to see, though. Don't try this at home. I've had students, I'll tell you what I've had students do in a minute. Okay, what you do is now this has oxygen in it. So I'm going to take this, I'm going to put it under here. I want you to watch the flame. It should get brighter. Ah, there's not enough oxygen in it. Oh, could you see it? It got a little brighter. Let's try it. See if we can get some more. I don't know why it's got to be that the yeast aren't doing very well because this thing should blow up. That's what I get for thinking my yeast was in good shape, huh? Let's try it with this one. Because we're putting it in a smaller space. Try to catch some more. Okay, let's try this one. I'm going to try it in a smaller space and see if maybe you guys can see it. Watch to see if it gets brighter. Nope, just blew it out. Didn't work. I'm not giving up that easily. Hang on. Because I've seen this actually, I mean, it really lights up. And I'm really having a problem getting the oxygen.
I think it's your yeast.
Yeah, I think so too. Ooh, feels like it's in there. Ooh. Ooh. I'm gonna, would you put this on here when I let it go? Ooh. It's okay, go ahead, put it on there, please.
It's not poison.
Watch everybody, watch.
Yep.
No, crud. Wait a minute, I still have some in here. Light me up. Light me up. I am so not giving up.
Oh boy.
Thank you. Okay, I gotta let it in there, but not fast enough to blow it out. So let's see. There, see it? See it get lighter? Yeah. Woo! Praise the Lord. That was like pulling teeth. What do we see there? Boy, was that hard. We saw that when there's more oxygen, then the fire burned a lot brighter, didn't it? And if I told you, I'd tell you, I had students once do that, and they let the balloon go. They like had a balloon full because the yeast worked correctly. Yeah, and they had a balloon full, and they let the balloon go too fast. And we watched the fire run down the jar, up the balloon, and to their hands. And it almost burnt the place down. I mean, it was bad. All of us were like standing there freaking out. I go, okay, that's the last time I have the students do that experiment. That's not happening again. I will demonstrate it for them because I'm a mess anyway. Anyway, but what we saw there was that oxygen is required for combustion. If you get rid of the oxygen, fires don't burn. But if you have too much oxygen, fires burn too quickly, and that's why they can burn our bodies up. They can cause more forest fires, etc. So God diluted the atmosphere with the nitrogen. Very, very important. The atmosphere, besides just keeping us alive, has another very important job. It actually keeps the temperature nice here on planet Earth. How many of you have ever seen the movie Frosty the Snowman? You guys ever seen it? Okay. Do you remember in the movie Frosty the Snowman how when she's going to take him back to the North Pole that she gets really, really cold? And what does Frosty do to take care of the little girl when it gets really, really cold? Where does he put her? Puts her in a greenhouse. That's right. He puts her in a greenhouse because he's going to help her out. Well, believe it or not, the atmosphere does something called the greenhouse effect. You may have heard of that before, and it's a good thing. The greenhouse effect is a very important thing because what happens is when the sun's warmth hits planet Earth, then it bounces back and forth in here and gets caught because of the greenhouse effect. Some of it does escape back to outer space, but a lot of it is caught by the greenhouse effect, like a greenhouse. In Frosty the Snowman, when he put her in the greenhouse, even though it was cold outside, it was warm in the greenhouse, right? And so the average temperature on planet Earth, if you take the North Pole, South Pole, everything in between, and you average all the temperatures on planet Earth, the average temperature is 50 degrees Fahrenheit. That's fairly comfortable, isn't it? I mean, 50 degrees is fairly comfortable, especially when you consider North and South Pole, right? So this is very important. Now, I want you to understand this because some people will go, well, but it's the right temperature because we're just the right distance from the sun, 93 million miles. But the moon circles around us 240, I'm pretty sure it's 240,000 miles away. And so it should be close to the same temperature as we are, but it doesn't have an atmosphere. So if you're standing on the moon, the side that's heading towards the sun is over 200 degrees Fahrenheit hotter than the side of your body facing away from the sun. You get that? So it's not just the distance from the sun. We're the right distance from the sun, and we have just the right atmosphere, because without having just that right atmosphere, we wouldn't be able to hold in the heat and we wouldn't be able to breathe. Okay? Wow, we're seeing a lot of design features here, aren't we? Right? So the greenhouse effect is very, very important. Now, the atmosphere, when we study it, scientists like to break things apart and classify them. So we break the atmosphere into parts. The lowest part of the atmosphere that is closest to where we live, so we'll put a little tree here, we'll put a little person here, how's that? They're smiling, okay, there's a smile, whee, okay. What do we call the layer of the atmosphere that we live in? What do we call that layer? Look at your book. What do we call the lowest layer of the atmosphere? Good, troposphere. Troposphere. Okay. And so that's where most of the air actually is. The particles that make up the air are held by planet Earth by the gravity. And so the closer you are to the sea level, ground, the more air there is because the gravity pulls on it harder. The higher up you get, the less air there is because the less the gravity is able to pull on it. So if you've ever been up on the top of a mountain, there's a lot less pressure, therefore there's less air than there is at sea level. Does that make sense to everybody? And because the air actually has mass, it takes up space, it's matter, it actually weighs something and it presses down on everything underneath it. Let's go back to the different layers of the atmosphere. So we're told that basically the first 7 miles of the atmosphere is the troposphere. What happens here where we live? What kind of things do you see happening in the troposphere? And it mentioned it. Sometimes the troposphere is called the weather layer. So what do you think is in the troposphere that we don't see other places? What makes weather, guys? Think Floridians. What makes weather?
Water.
Water in the air. Thank you. So there's a lot of water in the air in the troposphere, and that's why it's the weather layer. Here we have clouds and things. But when you get into the next layer, you don't have the water vapor, therefore you don't have the clouds and stuff. Somebody tell me what's the name of the next layer up? Stratosphere. The stratosphere. Now, the stratosphere has a couple things going on there. Once again, there's not weather there, but there's a couple other things that are in the stratosphere. What? Go ahead. You have the jet stream up there. The jet streams are actually high-speed winds that go from west to east. If you've ever seen that on a weather map where they show the wind dipping and stuff like that, they're showing you the jet streams because the jet streams will carry the weather underneath it frequently. And the jet streams, when I say high-speed winds, I'm talking over 200 miles an hour, okay? And so a plane that's flying from California to New York would love to go catch the jet streams as a tailwind, you know, and they'll come in early on a 30,000 mile flight because they've got this tailwind that's 200 plus miles an hour, 250 miles an hour pushing them, jet streams. But then the opposite is true. If you're going from New York to Los Angeles, then you want to dip under the jet streams because you don't want to be in a headwind the whole way over there that's 250 miles an hour pushing against you, right? Okay, so the jet streams are in the stratosphere. Another thing that's found in the stratosphere, and the jet streams do push around the weather underneath them to a degree. The other thing that we find is what? There's something in the stratosphere that protects us. Yes, Angelina?
The ozone.
Very good, the ozone layer. The ozone layer protects us, like we talked about before, from ultraviolet radiation. So without it, everything on planet Earth would die. Ultraviolet light kills things. When I used to work in cancer research, I worked in a Lamination Hood, which is a place that's totally sterile. And it looked like a huge fish tank, okay? Huge stainless steel fish tank with this big piece of glass that pulled down. And when I would work in it, I would pull up the glass about that far just so I could get my hands in it. And like it went all the way to the ceiling, but it was all stainless steel, and it had this big piece of glass right here, okay? And when I would work in it, I would raise the glass about that far. I would click on the light, the regular light, and the flow. There was an airflow that would literally push a curtain of air right down in here. So when my hands went in, nothing else could get in there with it. It would suck it in the air because it was a sterile environment. And when we got done working in the hood, because that was the only way you could make sure, we were working with clones and things, and so it got very expensive. So you had to keep them from getting infected by anything else. And when I would get done working in the hood, we would wash it down with alcohol in case anything got out, while I was working. And then we would shut the glass. We'd turn off the flow so it didn't make a vacuum and break the glass. We would shut the glass, and then you would flick on the UV light. And when nobody was working in there, you had a UV light in there at all times because it would kill anything that might still be in there. So see, ultraviolet radiation is very deadly. It's too high energy for living things. And so God had to put the ozone layer up there so that it could protect us from ultraviolet radiation. But do you know what? If ozone was down here, does anybody know why that can't be? We can't have ozone down here. It's a pollutant. It'll kill you. If we breathe a lot of ozone, it will kill us. Yet God used ozone to protect us. So what did he do? He put it 18 miles high. So it's not bugging anybody. Pretty cool, huh? Boy, do we see God's protective hand in all this over and over and over again? Matthew.
You worked with clones?
Yes, sir.
Cool.
But no, we were cloning tissue culture. We were cloning cells. We weren't cloning full organisms. We would actually develop cell lines because we were trying to get cell lines that would make the particular antibodies we wanted. Because then when we made those antibodies, we could make something called an affinity column so that we could pour things through and the antibodies would grab the chemicals we needed and pull them out. And so the process of doing these experiments would take 6 to 8 months to do from start to finish. Think about that, okay? And yes, once we found, I'll tell you real quickly, we would have to inject mice with a particular chemical that we wanted their body to respond to. Then we'd have to kill the mice. I don't know if they can even do this still now. We'd have to kill the mice because then I'd have to harvest their bone marrow cells. I hated bone marrow day because I had to snip off the heads of 40 little mice, and then I had to take all their little legs in little sterile containers and carry them back upstairs, and then under a fume hood I would have to take with forceps because I couldn't touch them because you had to stay sterile. I'd have to take each of their little legs and scrape off all the meat, and then I'd have to take the little bone and I'd have to put a needle in it and squirt it into a test tube so that I could get their bone marrow cells. Then once we had the bone marrow cells, we would have to plate them out because then we would culture them or grow them in an incubator in little containers, 96 well plates. It's a little plate with 96 little wells on it. Then I would have to test those to see which of those, because you would dilute them, so you only had like a couple cells in each plate, each well, and then I would test each well to see if that cell was making the particular antibody we were looking for. You see why the experiment takes 8 months? Because you have to grow this stuff, then you'd have to test it, and I'd test those to see which cells were making the antibodies we were looking for. Once you found the cells that were making the antibodies you were looking for, you would clone that cell. You would put that cell into production. So you would pull that cell out of there, you would put it into other containers, sterile containers, and you would start to grow those cells. And you'd grow them and grow them and grow them, and then you'd spin them down and you would pull the antibodies off the top because it'd be in a liquid culture, so you would pull the liquid off the top, hoping that the antibody you were looking for is in there. And then you would test them again because sometimes these cells that were originally making the antibody would stop making it. Other ones would continue to make it. And then once you got them, then you would go through the process of concentrating the antibodies, and then you go through the process of attaching it to the things in the affinity column, and then you go through the process of, it was a very long process. It took months. Anyway, it was interesting. It was interesting. When I got my degree, I actually got to use a lot of the information to work in cancer research, and it was fun to use it for a couple of years. I wouldn't want to do it forever. I don't know about you, but I can't stand being inside all the time. I used to go outside just to eat lunch, I gotta see air and sky. You know what I'm saying? It just drove me nuts. I'm one of those. If I didn't teach homeschoolers, when I was teaching at the Christian school, I used to take my classes outside certain times. I couldn't stand it. I just couldn't stand being inside all the time. It just drove me nuts. I'm like a wild animal. I'm sorry. Anyway, okay. So that's why see, they gave me the room with the big windows because they don't want me to go nuts, Anyway, all right, let's go up. So when we go above the stratosphere, what's our next level? Look on there. Mesosphere, right? Now you see a lot more words on there. That's because when you get to the place where it's stopping being the troposphere and it's turning into the stratosphere, they call it the tropopause. Pause just means something is ending. So the troposphere is ending, so it's called the tropopause, okay? When the stratosphere is ending, it's called the stratopause because the stratosphere is ending. When the mesosphere is ending, it's called the mesopause. Does everybody see? That's those extra words, so don't let them get you hung up. Okay, the mesosphere, what do we know about it? It's cold. It's really, really, really cold. Now the book talks about as you go up in the atmosphere, it gets colder and colder. Anybody that's been up on a mountaintop knows that, right? It gets colder and colder, and that's why in the planes they have to pressurize them, and they're not only pressurized because of the lack of atmospheric pressure, but they also keep you warm, don't they? So, but as you go up, when you get to the ozone layer, the temperature actually starts increasing again because the ozone layer is catching all that radiation from the sun, and it actually warms it back up. So it's not under freezing, even though it's way up there. But as soon as you get to the other side of the ozone layer, the temperature like dives. Really scary dives, like no place on planet Earth dives. Way cold, okay? And notice over here, there's the ozone layer, but notice over here you have the ionosphere, which you read about, and the ionosphere overlaps between the mesosphere and the exosphere. The exosphere, most people would consider outer space. The molecules there actually are orbiting orbiting planet Earth. They're so high up. And there is an area called the thermosphere, and the thermosphere is up there. See, it's up there, overlap. I guess the ionosphere is in the mesosphere, and it's the thermosphere that overlaps the exosphere and the mesosphere. The thermosphere is called that because thermometers work by telling you how fast a molecule is moving. Did everybody just hear what I said? Thermometers don't tell you how hot something is. This is how we think of it. Thermometers tell you how fast a molecule is moving. So a thermometer is really a molecular speedometer. Did you get that? So if a molecule is moving really, really fast, it says that it's hot. If it's moving really, really slowly, it says that it's cold. Okay? Maybe I'll show you that next week. But I'm not set up for that experiment. But I can show you that. Okay? And so when something's hot, the molecules are moving more quickly. Well, it gets colder and colder and colder as you get farther and farther from the planet Earth. But in the thermosphere, remember I just told you that the molecules are actually orbiting planet Earth? The molecules are going so fast that if they hit a thermometer, they'd be very, very hot, over 200 degrees. In some places I've seen up to 700 degrees. Really, really hot. But there are so few molecules that if you're standing up over at the thermometer, it would say it was really, really cold, even though the few pieces of the atmosphere that are there are actually going really fast and therefore really hot. So in other words, the temperature is very confusing in the thermosphere, and that's why they call it the thermosphere. Okay? Now the ionosphere, you got a different thing going on, and we'll play with that. Let's play with that. Okay, so we talked about that. Oh, and here shows you the temperature. As you go up, the temperature goes down until you get in the stratosphere, and then it levels back out. And we already talked about the higher you get, the colder it gets, and that's why you see snow and stuff that stays snow year-round on the tops of mountains. Here's the temperature once again. You go up, it goes lower and lower and lower as you go up in the, see down here, from 0 degrees to -60. So the higher you go, the lower the temperature goes until you get to the stratosphere, and then it goes back over, and goes back over because of the ozone, but then when you get past it, whoom, it goes down really, really fast. Planes tend to fly, spy planes and stuff like that tend to fly in the stratosphere. Weather balloons are up here. Most planes, commercial jets, will be right at the edge, depending on whether they're going east or west. They want to catch the tailwinds or not fight with the headwinds, depending on which way they're going. When you see a cloud, have you guys ever seen a thunderstorm that looks like this, where it looks cut off at the top? You ever seen one like that before? Oh, guys, you need to get off your phone and start looking at the clouds more. Okay? Start looking at the clouds. When you see a cloud like that, the reason it's whacked off at the top, they're called an anvil cloud because it looks like what a farrier does the horse's horseshoes on. It's flat at the top. They're called an anvil cloud, and they look like that because they've just hit the 7-mile part. They've just hit the stratosphere. They're so high that the top of that cloud is in the stratosphere, and the winds just sheared it right off. Isn't that cool? So now you know what you're looking at, okay? This weather's going to be fun to study. You know why? Because you can look up and observe this stuff all the time. And that's what's so fun about weather, is that you can actually see it going on around you. So it's pretty fun. This shows you the jet streams. You see, that's what they're showing you here is when they show you the jet streams. And these jet streams actually move these weather fronts down here, and we're all sitting here going, high pressure, come on, high pressure, come on. Well, the reason high pressure brings cold is because hot air rises, doesn't it? So when it rises, there's less air pressing underneath it, so it's a low pressure system. Cold air sinks. So it presses harder on the ground underneath it, therefore it's a high pressure system. Does that make sense to everybody? So that's why we're all going, come on H, right? We want some cold weather to come down to us. Okay, that's just one of the kind of planes, like the supersonic planes definitely fly in the stratosphere because they want to be above the weather. They don't want to be down in the weather. I just told you that the faster a molecule is moving, the higher temperature it is. When, I'm not sure if we need that yet, so we'll just come back to that. When something is, that looks cold to me, doesn't that to you? Looks like ice cream? When something is cold and the air around it is warm, it'll actually absorb the energy, or in other words, it will warm this up. Won't your ice cream melt? Right? Won't your ice cream melt? Because it absorbs the heat around it, doesn't it? Or if your glass of cold water, it's going to get warmer as it sits there. What about the opposite? What about if you, oh, that was that one. So that, I guess, was supposed to be warm. But what about if you had a hot chocolate? If you had a hot chocolate and it was a cold day, would it stay hot chocolate very long? No, it would give its energy to the air around it. So that's actually what heat is. Heat is actually the movement of the energy from one place to another. So ice freezes because of heat. Water freezes because of heat. Because if heat is actually, see, remember you're in science class and things are always weird in science. If heat is actually energy moving from one place to another, for water to freeze, the energy has to move out of the water and then it can freeze into ice, and that's why ice freezes because of that. Now we can go back to this other picture. Let's think of water for a minute. Hang on just a sec. Don't forget your question. Water is a liquid. When we think of it as water, the molecules in liquids are dancing. They've got enough energy that they can dance. And we know that because they pour. They will take on the shape of whatever container they're in, don't they? If we freeze the water, we're taking the energy out so that these dancing molecules will actually be going like this. They still vibrate, but they can't move anymore because they just don't have enough energy. And that's what makes them a solid. Let's go the other way. So we have our ice, and we give it energy, and it starts to dance around, okay? And then if we keep giving it energy, it'll actually become gas. Gas is something that has so much energy, it starts bouncing off the walls like a little hyperactive kid that's been given a Coke and some birthday cake. You know what I'm saying? Boing, 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 boing. You can't tell I have a child like that, can you? And so that's what a gas is. And believe it or not, guys, what I just described to you, you'll hear me teach you again in physical science. You'll hear me teach it again in chemistry. You'll hear it again in physics, because that is the kinetic theory of matter. That is actually scientific, how we look at matter. Matter can either be a solid, dancing liquid, or pink, 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 a gas, okay? So when the air goes through these processes, it actually makes these changes. I don't think you need that picture. Well, we already talked about that the UV is caught by the ozone. Trying to think of what else. Oh, the ionosphere. That's where I wanted to go. I knew I was looking for something. Okay, normal atoms, I'm going to erase this. By definition, an atom is electrically neutral. It doesn't have an electric charge. That's what it means by electrically neutral. How does that happen? Well, in the nucleus of the atom, you have positive charged protons. And then outside, orbiting way outside, you have little negatively charged electrons. And then there are neutrons, but they're neutral, and they're also in the nucleus of the atom. So far, so good? Little atomic theory here? Okay. Now, if an atom gains or loses electrons, it is no longer called an atom. It's called an ion. Because once it gains, let's say it gains an electron. Now, it's got 2 minus signs plus 1 plus sign. So what's its overall charge? -1, right? There's 2 minuses, 1 plus is going to be a -1. So it'd be a negative ion. Let's go the other way. I'm not going to give you the name because I don't want to confuse you. What happens to hydrogen a lot, this is a hydrogen. That's what actually hydrogen looks like, 1 proton, 1 electron in nature. Let's say it loses its electron, which happens a lot to hydrogen because it's a little bitty guy, so the bullies just all come steal his electron on a regular basis. So now what's his charge going to be? Well, he doesn't have a positive and a negative anymore, so now he's going to be a +1, isn't he? Right? Once an atom loses or gains electrons and has a charge, it's no longer called an atom. It turns into an ion. So an atom is a particle that used to be an atom, but now it's got a charge. It's got an electrical charge. You with me so far? Okay. In the ionosphere, the gases are high enough up there, and the sun's energy has either ripped away or added some electrons, depending on which chemical is there and what's happening to it, and it gets an overall charge. That's why it's called the ionosphere. And you can bounce shortwave radio waves off of it. Have any of you ever played with a shortwave radio? No, they're kind of passé now because you can go on the internet and talk to people all over the world. But when I was a kid, you couldn't do that. You couldn't talk to somebody on the other side of the world unless you had a shortwave radio. And my brothers built one. That was before they regulated them and took it. Everybody couldn't just use the shortwave radio. And my brothers would get on the shortwave radio in Miami, and we would hear the news in London, and we would hear Big Ben, and they could talk to people all over the world. And that's how missionaries used to talk to somebody that was way far away, because there were no satellite phones, there were no cell phones, there were none of that stuff. And so you would use shortwave radios because you could bounce the waves off of the ionosphere and back down to other places. How many of you have ever noticed that when you're on a trip and you're listening to a radio station, when you get far enough away, you lose the radio station. You have to go find another station, right? That's because the waves don't bounce off of anything. And so as you go over the curve of the Earth, and here's the radio station, and as you're traveling over the curve of the Earth, eventually you can't get the waves anymore. Does that make sense? They just go right off into space, and you have to find another radio station. But see, short waves can actually be bounced off the ionosphere, which is a big deal, so that you can actually get it to go boing, 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 and you can talk to somebody on the other side of the planet with shortwave radios. Okay, that's kind of how satellites work now, isn't it? Because they've got a satellite up here, and you bounce the wave here, and then you bounce it back down here. So we've just kind of made a man-made version of that to use. And then we don't even use that now. How do they use where they've got certain types of light and glass, that fiber optics, that's it. And they use fiber optics now, and it's a type of glass where the light can't get out of the glass. Have you ever seen a fiber optic cable? It's really cool because you turn it on and the light just goes right here and no place else. It somehow keeps the light in, and now they've got it so when you talk on the phone to Alaska or someplace like that, it's moving at the speed of light. That's why there's no hesitation anymore. When my sister used to live in Alaska and I'd talk to her, it was like talking to her on a boat radio. Hey, how you doing? Fine. How are you? Fine. You know, that's what it used to be like. And then when they got fiber optics, because it was moving much slower, they got fiber optics and started moving at the speed of light. Well, now you can talk to somebody on the other side of the world. It sounds like they're in the next room. It's just as fast, you know, woohoo. It's really cool. See, you're not old enough to appreciate that. Anyway, okay, so see, you have these ions. And when these ions, when certain times of the year, when the particles get excited, and it explained this, we have the aurora borealis and the aurora australis. The aurora borealis is the northern lights, and the australis is the southern lights. And once again, let's see. Here it's described in the 4th edition, it's on page 12, but it's not a picture, it's just described. And it says there that, we already talked about that, within this layer, the exosphere, lies the magnetosphere, and things get trapped in the Earth's magnetic field near the poles is where this happens. When these particles collide with each other, they give off energy, which energy translates into these pretty lights. Do you remember when we burned those different chemicals and we got all those cool lights? Okay, so you've seen this before, that the different particles make different lights. And so that's what actually makes the northern and the southern lights. I would love to see this sometime. How about you? I mean, it's just hard to believe that you can look up and see all these colors. It's very, very cold usually where places are that you can do this. So anyway, and this just shows you the magnetic field of the Earth. It doesn't have, interesting. It doesn't have a magnet in it. That's really interesting. Doesn't have a magnet in it, but it kind of acts like a magnet, and that's wow, this whole thing must have been a presentation that I was grabbing these pictures from. And it's by NASA. Interesting. Anyway, okay. That's actually a picture from NASA. This shows you, see here's Antarctica. Can you guys see it? Antarctica? And can you see the southern lights here? Isn't that neat? Seeing them from outer space? That's pretty cool, huh? So, and we paid for that with our tax dollars, so we're allowed to see that. We're allowed to use these pictures. Okay. When you get up into the thermosphere and stuff, that's where your satellites actually go. The shuttle missions are actually in the exosphere. So that's why I said even though we count the exosphere as part of the atmosphere, most of us would consider it outer space.